In this video, we are going to practice those discrete probability concepts we learned in our last video. So obviously we're going to talk about probability, then we have to talk about the lottery because that is, something that clearly relates to probability. So let's say this particular lottery, I can win if I match 5 digits in order to 5 randomly drawn digits. So remember, whenever they talk about digits, they're talking about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 through 9, and there are 10 digits, the digits 0 through 9. So if I'm looking for the probability of winning the jackpot, there's only one winning combination, just one. And so my probability of winning is 1 out of, and then my question is, how many different ways can this happen? Well, I have 10 digits 5 times. So it's 10 digits for the first draw, 10 for the second, 10 for the third, 10 for the fourth, 10 for the fifth, or just 10 to the fifth obviously is the easiest way to write that. So it's 1 over 10 to the fifth, which turns into 1 over 100,000, or as a probability as a decimal, 0.00001. So 1 in 100,000 that I will win. And this is actually a pretty nice lottery because a lot of them are worse. And this makes it even nicer. Let's say they're going to give me my money back if I match at least one digit, which means I could match 1, I could match 2, I could match 3, I could match 4, or I could be the big winner and match all 5. But my question is, what's the probability that I don't lose my money? Which means the best idea here is, instead of finding the probability of matching 1 and 2 and 3 and 4 and 5 and then adding all of those together, would be the probability of at least 1 would be 1 minus the probability of not matching any. So this is where this little rule is going to come into play because it's going to be so much easier. So I'm going to take 1 minus, and then I have to look at, well, what's the probability that I don't match? So again, I can look at this as there are 100,000 different ways, but what's the probability that I don't get the correct answer? Well, the first time it's 9 out of 10, the second time it's 9 out of 10, the third time it's 9 out of 10, etc. You see where I'm going with this. So really, it's just 9/10 to the 5th power, or 0.9 to the 5th, and that ends up giving me 1 minus 0.59049, which turns into 0.40951. So there's about a 41% chance that I don't lose my money, which means you know that I totally made up this question because no lottery would do that. We're going to take a look at a couple of probability questions now involving a deck of cards. And so if you've never picked up a deck of cards before, you probably don't know the little facts that I've written in pink. And if you have, you're like, duh, I already know all of this. But let's just make sure, for the people who maybe have never played cards before, there are 52 playing cards in a deck. There are 4 of each type, and those types include ace, 2, 3, 4, all the way up through 10, jack, queen, king, ace. And there are 4 suits. Those suits are hearts, diamonds, clubs, spades. And there are 13 cards in each suit. So I've also included a formula there for us to use, which I'll talk about in just a moment. I want to talk about this question, the probability of selecting a hand of 5 cards. Of course, that would be like a poker hand, for those of you who play cards, that has an ace, king, queen, jack, 10. So I'm not worried about the specific suit of the card. I'm saying any of the aces, any of the 4 kings, any of the 4 queens, etc. So most students would correctly begin this question. And again, there's more than one way to do this, and I'm going to show you 2 ways. And the first way I do this is not my favorite way, but it's the way that a lot of students would begin this question. They would say, well, in order to get an ace, there are 4 aces out of 52 cards. So 4 aces, 52 cards. And then the next time I draw, there are 4 kings, but here's where this guy comes into play. We're saying the probability of B, or the probability of selecting a king out of the deck, assuming that I've already chosen the ace. So the probability of getting a king is there are 4 kings, but now there are only 51 cards because I'm assuming that I've already chosen an ace on my first card. And then there are 4 queens, but only 50 cards because I'm assuming I've already selected both an ace and a king. And then there are 4 jacks, but only 49 cards, and there are 4 tens, but only 48 cards. And a lot of students would stop there, and unfortunately that's incorrect. This is a really good start to this question, but it's not the end of this question. Because the way that we've calculated this assumes that we've first chosen an ace, then a king, then a queen, then a jack, then a 10. And we know that in a hand of cards, it doesn't matter the order in which you receive the cards, it matters the cards that you have in your hand. So then we have to think about the number of ways that this could occur. So let's just say the order matters. So we're going to say this is the number of ways it could happen. I'm sorry, this is the probability that it could happen, but I now need to find the probability the permutation 5, 5. And what I mean by that is the first card that I draw, if I have 5 cards, I have 5 choices for the first card, either the ace, king, queen, jack, or 10. Then I have 4 cards left for my second card that I get, and 3 choices left for my third card, and 2 and 1, which is the permutation of 5, 5. So you can either write permutation 5, 5, or we're just going to put 5 factorial because that is what we're doing. So that is a correct answer. So I'm going to go ahead and box that one off. This is a correct answer. The problem with the first answer is that a lot of students forget about the 5 factorial. They forget about the fact that we've calculated it for one specific order and we need to take it times the total number of ways that we could choose that. So the way that I like to do this instead is, and it's going to give us the same answer, and I'll verify that for you as we go through it, but the way I like to do it instead is using those binomial coefficients. So we're going to say that in order to get this hand, my numerator is going to be, there are 4 aces, I choose 1. There are 4 kings, I choose 1. There are 4 queens, I choose 1. Whoops, don't make it a fraction. I choose 1. There are 4 jacks, I choose 1. And there are 4 tens, I choose 1. And the denominator is that there are 52 total cards, and I'm choosing 5 of them. Now, you might be thinking, well, that seems too easy, and it does seem too easy, but it is the correct solution. So let's take a look at this solution. 4 choose 1, if you'll recall, is 4 factorial over 4 minus 1 factorial, 1 factorial. Let me try that again, 1 factorial, which means 4 times 3 times 2 times 1, and then 4 minus 1 is 3 factorial, so that's 3 times 2 times 1, and then obviously 1 factorial is 1. So I end up with 4 over 1, or 4. So really what I have in my numerator is 4 to the 5th power. And what I have in my numerator here is 4 to the 5th power also. So now let's look at the denominator. My denominator says 52 choose 5. So 52 choose 5 is, I should use a different color here. Up here, we'll just use 4 to the 5th. So now, 52 choose 5 is 52 factorial over 52 minus 5, or 47 factorial, 5 factorial. And 52, just this part of it right here, if you'll recall from our video where we learned about permutations and combinations, we said, well, this would be 52 times 51 times 50 times 49 times 48 times 47 factorial, and that 47 factorial would cancel with the 47 factorial on the bottom. So now I have over 5 factorial. So down here I have 52 times 51 times 50 times 49 times 48, because the 47 factorial canceled out, divided by 5 factorial. Which means what I really have, and again up here we had, that looked like a 45, 4 to the 5th. On the bottom we have 52 times 51 times 50 times 49 times 48. And then what happens here is I got a fraction, and then I'm also got a fraction within my fraction, and we all know that means multiply by the reciprocal. So this is really 5 factorial and then 4 to the 5th over 52 times 51 times 50 times 49 times 48, which is exactly what I had here, because I had my 4 to the 5th, I had 52, 51, 50, 49, 48, and then I had 5 factorial. So notice both answers result in the same solution, and the reason I like this guy better is because it's really easy for me to use my calculator. Instead of having to type everything in, I just use my calculator to say 4, choose 1, which of course gives me 4. That's where I got that 4 to the 5th. And then this guy, I just do 52, choose 5, and calculate that result, and then I do my division. And so the 5 factorial is already sort of factored in there. And what I end up with is 4 to the 5th is 1024. And this guy, with the 52, 51, 50, etc. divided by the 5 factorial, gives me 8960, and which is approximately 0.000394. So that is the probability. So obviously that's a more complicated question, but that's the kinds of things that you should expect. Now let's take a look at the probability of selecting an ace 4 times in a row if the cards are put back in the deck. So if the cards were not put back in the deck, we would have a situation like this, where we would say 4 out of 52, or say 4 out of 52, 3 out of 51, 2 out of 50, 1 out of 49. And we don't really care about order. We don't have to worry about multiplying by some value here, because we're not saying that it has to be this ace first or this ace second. Now, that's not what they're asking, though. They're saying if the cards were put back in, well, then it would be 4 out of 52, and then I put the card back in, so there's still 4 aces out of 52 cards, and then there's still 4 aces out of 52 cards, and then there's still 4 aces out of 52 cards. So it's really just 4 over 52, or 1 out of 13, to the 4th power, which is approximately 0.000035. Let's take a look at another question dealing with cards, this time dealing with a full house. And for those of you who don't play cards, a full house is 3 of one type of card and then 2 of another. So for instance, 3 jacks and 2 tens would be a full house. Let's talk about different ways that we can find the probability, because you'll find as you're working with probability questions that there are many correct ways to find the answer, even though there's just one correct answer. So let's talk about some of the different ways that we could do this. So one way to go about this is to say the first card, the first type of card, there are 4 of them in the deck. So there are 4 jacks in the deck, and I'm going to choose 3 of them. And then there are 4 of the next type of card in the deck, and I'm going to choose 2 of them. And then, of course, there are 52 cards in the deck, and I'm choosing 5 total. So this is close. This is at least showing some mathematical reasoning. But the problem with this is I didn't specify which card I'm choosing. So just like we did in the first part of my last example, I said we're going to use some sort of permutation. And the permutation on the last example said that there were 5 cards and we didn't care which one came first. Well, in this case, there are 13 different cards, and I'm going to be using 2 of them. So what happens here is I get 13 times 12, that's the permutation, and then times 4 choose 3, if you'll recall, is 4 factorial over 3 factorial 1 factorial, which is just 4. And then 4 choose 2 is 4 factorial over 2 factorial 2 factorial, which is 6. And then 52 choose 5, I actually computed on my last example, so we're just going to go right to that value, 2598960. So 2,598,960. That gives me as a numerator 3,744. As a denominator, same 2,598,960, which is approximately equal to 0.00144, or about 1.44%. Now let's look at another way to do the exact same question. So again, I probably would not choose that first way, again, because this part can get tricky for a lot of people. So let's look at another way to do that same question. The numerator could be that I have 13 different types of cards, and I'm going to choose 1 of them. And then for that for that type of card, there are 4 of them, 1 of each suit, and I'm going to choose 3 of them out of the deck. Then there are 12 different types of cards left, and I'm going to choose 1 of them. And for that one, there are 4 cards, and I'm going to choose 2 of them. And my denominator is, of course, 52 choose 5. So doing this math, 13 choose 1 is 13, 4 choose 3 is 4, 12 choose 1 is 12, and 4 choose 2 is 6. And we already knew this was 2,598,960. And again, we get the same result, which is 0.00144. So that is another correct way to do it. You can also, and yes, you could have stopped right there with the first one or with the second one, but let's look at one more just for fun. You can also say, hey, I'm going to choose 2 different kinds of cards. 13 choose 2. So there's 13 different kinds of cards. I'm going to choose 2. Then, out of those 2 different kinds of cards I've chosen, I'm going to choose 1, and for that 1, there are 4 cards. I'm choosing 3. And then for the 1 that's left, I'm going to choose that, and for that card, there are 2 that I'm going to choose. Again, over 52 choose 5. And again, what's going to happen is we're going to get the exact same result. We're still going to get 0.00144 or 3744 over 2,598,960. So there's 3 different correct ways to think about the exact same question. Let's take a look now at a bit string question. And the reason I like this question is because it's an at least question. And these tend to throw students off, so I like to make sure we get some practice of those. So when I'm dealing with this question, it says a sequence of 10 bits, and again, bits is just a string of zeros and ones, is randomly generated. What is the probability at least one of those bits is 0? So if I didn't use my little at least formula that we talked about in our last video, then I would have to find the probability of 1 bit, a 1 0 bit, the probability that I had 2 0 bits, that I had 3 0 bits, that I had 4 0 bits, that I had 5 0 bits, that I had 6 0 bits, or 7, or 8, or 9, or 9, or 10. Now let's think about the sample space here. The whole sample space is that I have 0 0 bits, or 1, or 2, or 3, all the way up to 10. And so instead of doing all of this work to calculate all of this, I know that the sum of the sample space is 1, so I'm going to find the probability, at least 1 0, is 1 minus the probability that I have no zeros. 0 zeros, this guy. So if I take 1 minus that, it's going to give me everything that I have circled there in green. Now, this one shouldn't be too difficult to compute. So I have 1 minus, and then let's talk about the probability that I have no zeros. If I have no zeros, then that means that they're all ones. So how many different ways can I have all ones? Just one way. How many total, because again this is a probability, how many total possibilities did I have? Well, if it's a 10 length of 10 bit string and each value is either a 0 or a 1, remember we talked about that before, that's 2 to the 10th. That's the number of total bit strings available. So 2 to the 10th, 1 divided by 2 to the 10th gives me the probability of just getting all ones. 1 minus that gives me my solution. So this is 1 minus 1 over 1024, or 1023 divided by 1024, and of course I can also find that as a decimal. All right, let's take a look at the next one. What's the probability that a positive integer not exceeding 100 is divisible by either 2 or 5? So again, I'm looking for either 2 or 5. This or tells me that I'm going to have addition. And I also need to think about the fact that we have this formula, probability of A or B is equal to the probability of A plus the probability of B minus the intersection. The intersection being anything that's divisible by both 2 or 5, like 10 and 20, etc. So here's how we would go about this. I'm going to find, first of all, the denominator. So here the denominator again was 2 to the 10th because there were 10 values and they each had 2 options. The denominator here is a positive integer, which means we're starting at the value of 1. We don't start at 0. Not exceeding 100, which means 100 is included, which means there's 100 total. So that is going to be my denominator, is 100. That's the easy part. So this is the probability of 2 or 5. And now I need to find my numerator. So my numerator is how many values are divisible by 2. And here we actually get to use the floor function. So we've talked about the floor function before. 100 divided by 2, floor function, will give me the number of integers divisible by 2. And then the number of values divisible by 5 is the floor function of 100 divided by 5. And the ones that I counted twice, the ones that are divisible by both 2 and 5, I just take 2 times 5 to get 10, and that is the floor function of 100 divided by 10. Now, in this case, does it matter that I use the floor function? No, because 100 is in fact divisible by 2 and by 5 and by 10. But keep this little strategy in mind, because if I asked you for the probability that the positive integer is divisible by 3 or 7,
those are not going to be whole number values, and that floor function would definitely come into play. But let's go ahead and continue with this. 100 divided by 2 is 50. 100 divided by 5, 20. 100 divided by 10. Oops, I put a plus there. I apologize. This is minus the intersection. So now I'm going to subtract the 10 that were counted in both categories divided by 100. So that's 50 plus 20 is 70, minus 10 is 60. 60 divided by 100 is 0.6.
Let's make a deal. How many of you have watched this show before? I know it's Wayne Brady now, but back in the day, the host used to be Monte Hall, which is why they call this the Monte Hall puzzle. This puzzle says that you've got 3 doors, and behind one of these doors is a fabulous prize that you want to take home. If you choose the correct door, you get to keep the prize. But once you choose a door, let's say I'm choosing door number 1. Once I choose a door, the host will then open one of the other doors that's not a winner. So say he opens up number 3, and 3 is not a winner. So the question is, should I stick with door number 1? Or is it better, based on probability theory, to switch to door number 2? So think about that for a minute and then we'll go over it together. So what did you choose? Well, you should choose to switch to door number 2. And here's why. When I chose the first time, my probability of winning was just 1 out of 3. Which, that's just typical. There's 3 doors, one of them wins out of 3. But now, if I switch, then my probability of winning is actually going to be 2/3. Because if I win, that means my initial pick was wrong. And if my initial pick was wrong, that's 1 minus 1/3, or 2/3. So basically, it's always a better deal to change, again, based on probability theory. So that's not saying for sure that door number 2 is the winner, but based on probability theory, essentially I'm giving you another 1/3 probability that you are going to be the winner. Again, we found that by saying that my probability of winning the first time was 1/3. And so the second time, I'm looking at I win if my initial pick was wrong. And remember, my initial pick was 1/3. And so if my initial pick was wrong, then 1 minus 1/3 gives me 2/3. That's my probability of winning now because they've already taken this guy out of the equation for me.
Coming up next, we're going to take a look at some probability theory.